All right, today we're going to do a quick run through of all of the analysis from the Carts and Masses labs, both part 1 and part 2. So we're going to start on part 1. And the first thing I want to go over is hanger weight, just to make sure that you calculated that correctly. Remember, weight is a force. Fw equals mg. So Fw being the hanger weight, m being the hanger mass, specifically the hanger mass, and g being acceleration due to gravity. So when we plug all that in, you get Fw, the weight, is equal to 0.050 kilograms, that's the mass of our hanger, times 9.8 meters per second squared. We use 9.8 in labs because it is more accurate. You would use 10 in quizzes and tests and things like that. But for lab, we want to be as accurate and as realistic as possible. So when you multiply those together, you get 0.49 newtons. Now I do want to say, if you used 10, that's fine. You should have 0.5 newtons if you used 10. Either way is fine for this time. Just make sure that you have one of those two answers, 0.49 or 0.5. And that's going to be the weight for every single trial in part 1 because you never changed the hanging mass in part 1. So the next thing you were supposed to do was fill in your predicted acceleration being force divided by mass. And in this case, the force is the hanger weight, so what you just calculated. And the mass is the cart mass plus the hanger mass. So what that looks like is the weight of our hanger, 0.49 newtons or 0.5, depending on how you calculated it. And then on the bottom, our mass, 0.250 kilograms, that's the empty cart, plus 0.050 kilograms. So this is the cart, and this is the hanger. We add those together to get the mass of our system. And so that's 0.49 newtons divided by 0.3 kilograms gives you a predicted acceleration of 1.633 meters per second squared, somewhere in that general vicinity if you used 10 for gravity. So let's look at the second one. Trial 2 would be 0.49 newtons divided by 0.500 kilograms plus 0.050 kilograms. So 0.49 divided by 0.550. So again, this is the mass of our entire system. The cart with the extra bar mass plus the mass of the hanger gives you 0.891 meters per second squared. And so continue on for trial 3 and trial 4 in the same way. Double check yourself and make sure that you did your math correctly. Next is the percent error for trial number 1. And for your percent error, your predicted is going to be what you start with. That's your actual or your perfect world scenario. If everything works exactly as it should, ideally, that's what it should be. So that's your predicted. Minus your measured, which is what you actually got from running the cart, divided by predicted times 100. So that's going to give us, here's our predicted acceleration for trial 1, 1.633 meters per second squared, minus my measured for trial 1, 1.037 meters per second squared. Yours may be different. It should be different. There's no reason why your numbers should be exactly the same as mine. And then divided by our predicted again, times 100. Double, triple check that you're plugging it into your calculator correctly. And in this case, we end up with 36.5% between what I should have, what I expected to have, and what I actually got. And it's okay if that's a big number. That's totally fine. You will have another percent error for trial 2 if you copied the lab setup as it was written, or trial 4, which is what I intended it to be, if you followed what was stated in the video. Either one is fine as long as you have two different percent errors with your predicted versus your measured. And there'll be large numbers, and that's okay. So then you should also have graphed. I'm not going to walk you through the graphing because there was already a video for that. But let's look at the questions now. So write the equation for Newton's second law. This should be in your journal, in your notes. And it's F equals ma. You could also put in here F net equals ma. Force is equal to mass times acceleration. Second question says to draw free body diagrams for the cart and for the hanger. So two separate free body diagrams. So let's look at our process. First you have to put the object. So here's my dot that represents the cart. Is there gravity? Yes. So there's a weight, a force of weight. Is it sitting on a surface? Yes. So there's a normal force. It's not slowly rising into the air or slowly sinking into the ground. So the normal force is going to be equal to the weight force. Is there anything pushing or pulling it? Well, yes, there's a string pulling it. So we've got a tension force. And it doesn't matter which direction you show this arrow pointing. But it specifically is a tension force because it's a string. You could leave it like that and it would be perfectly fine. In the ideal perfect world scenario, our tracks are completely frictionless. You can say that there's probably a little bit of friction opposing our motion just because we didn't end up with a perfect scenario. But either way is fine, either with a little bit of friction added or without. So let's draw our free body diagram for the hanger. Again, here's my dot to represent the hanger. Is there gravity? Yes, there's weight, which we calculated. We could add a number into this free body diagram if we wanted to. Is it on a surface? It shouldn't be, so there's no normal force. Is there anything pushing or pulling it? Well, yes, there's a string pulling it, and that's going to be pointed upward. That's our tension force. Now, if you notice, our tension force arrow is a little bit shorter than the weight. And that's because when you let go of the cart and the hanger, it fell down to the ground. So this force has to be stronger than this force. If they were equal, then the hanging mass would just hang there in midair when you let go of the cart. And the last question, do your results confirm Newton's second law? Why or why not? Newton's second law says that mass and acceleration are inversely proportional. When one goes up, the other goes down. So did your results confirm that? Now let's look at part 2. So again, finding the hanger weight. The hanger weight is a force. So hanger mass times acceleration due to gravity. This one's going to be a little bit different because we're changing our hanging mass this time. So we've got our first one, 0.050 kilograms times 9.8 meters per second squared, or 10, is equal to 0.49 newtons. But this time your hanger weight is going to be different for every trial. So you're going to go back in and replace this mass with whatever it is in the subsequent trials. So 0.100 kilograms times 9.8 meters per second squared is going to give you some other weight or some other force. And then so that's going to be different for every single trial. When you get to that point after you've done your graph, you've found your slope, and you're ready to do your percent error. I know I talked about this in the graphing video, but we'll go through it one more time. We're going to do our actual minus the calculated divided by the actual. And in this case, actual is the actual real mass of our entire system, which is 440 grams or 0.440 kilograms. That's what it should be. That's what it was. Here's our calculated. And I just made up a number that could be something close to what you have. If you've got anywhere in the kind of 300 to 600 range, to 0.300 to 0.600, that's perfectly fine. Hopefully you're closer to the 0.440 area, but anywhere in that range is fine. And then divide it by our actual again. So when you plug that into your calculator, that's a relatively small difference between these two numbers. So that gives us a negative 11.8%. It's fine to have a negative percent error. It just means that your result was a little bit higher than what you expected it to be. And again, same question. Do your results confirm Newton's second law? Why or why not? Well, in this case, Newton's second law says that acceleration and force are proportional, directly proportional to each other, meaning when one goes up, the other one goes up. So, do your results confirm that? The next question has some calculation, and I know I went through this in the video, but I'm going to run through it very quickly one more time. If your cart starts from rest and accelerates toward the end of the track, 0.82 meters away, how long does it take to get to the end? And again, we're using our data from trial 1. Your numbers will be slightly different from mine, but the process is the same. So we've got our time. We know that our VI is 0 because it starts from rest. Our D is 0.82 meters, that's the length of the track. And our acceleration is whatever you got in trial 1 from part 2 of the lab. In this case, I got 0.897 meters per second squared. We look at our equation sheet and we see that the only equation we can use is the square root of 2D over A. Plug in our numbers, and I get 1.35 seconds. Your result should be in that same kind of range, somewhere in the 0.8, 0.9 seconds up to maybe 1.5, 1.6. If you're too far away from that, you might want to go back and double check your math. The second part of that question, pardon my line there, what is the cart's velocity at the end of that track? So we're looking for final velocity. We've got our same givens. VI is equal to 0. D is 0.82 meters. We're using the same acceleration, 0.897 meters per second squared. I wouldn't use the time from the last question just in case you calculated it wrong. This will give you a better result. So when you look at your equation sheet, you see that there's one equation that uses VI, D, and A, and that is square root of VI squared plus 2AD. So when you plug that in, 0 squared is 0, plus 2 times our acceleration, 0.897, times our displacement, 0.82 meters. Take the square root of all of that, and you get 1.213 meters per second. Your result, again, should be somewhere in that general vicinity, anywhere from about 0.8 or 0.9 up to 1.5, 1.6 in that range. If you're too far out of that range, again, go back and double check your math. Now that you have completed all of the analysis, for both parts of the Carts and Masses lab, you're going to do two things. First, make sure that you've uploaded pictures of your lab for each of the last 2 days, for Wednesday and for Thursday. Second thing you're going to do now is to go take the Carts and Masses lab quiz, and that's going to be your wrap-up.